as I was saying, I've got some formulas that I got to write out, but that'll be for the end of the lecture. So we are back to energy balances, and we are going to be focusing on heats of vaporization to set ourselves up to do flash energy balances. So basically, in the back of your book, and in your thermo books, and in this process book, and a lot of other textbooks, there are property tables that include heat capacities, heats of vaporization, normal boiling point, Anton's vapor pressure, things like that. Right? So the one that we'll use a lot that isn't tabulated is going to be what is the heat of vaporization at states different from the normal boiling point. And that's what some of these rules are going to be. So we're going to first go over a review of our energy balances and then talk about how to predict the heat of vaporization at states that are not the normal boiling point. Right? So when you look in the back of the book, at 1 atmosphere, that's the temperature that it boils at. That's the normal boiling point. That's where they measure the heat of vaporization, but most all of our processes are not going to be at 1 atmosphere. So if we need to know how much energy it takes to vaporize something, we need to be able to predict it at any arbitrary state going from below atmospheric conditions to above atmospheric conditions. Okay? So let's do energy balances here. So for a closed system, delta U, Q minus W. All right, so this is a simplification of the general energy balance. I'm not doing the whole thing. For open at steady state, we can get delta H is equal to Q dot minus W dot, right? The difference between these is that you have a little bit of this PV energy that is pushing the fluid into the system, and then a little bit of PV energy where the system is pushing the fluid out of the system. So that is the difference there between those. Delta U can be obtained by unpacking the definition of C sub V, right? Whereas C sub V is equal to the rate of change of the internal energy with respect to temperature while holding the specific volume constant. Yes?
So that W that you have on the first two, can that be broken up into like work done by shaft and work done by expansion and contraction?
Yes. Okay. Right, so this is the definition of C sub V. We actually cannot predict this using classical thermodynamics. So what we've done in the system of thermodynamics is said, you know what, let's just measure this property because it's going to be really useful, right? So that's what they did. So what we're doing is we're just unpacking the measurement that someone else has already made. Delta H correspondingly, T1 to T2, C sub P dt. This is based on the definition of the heat capacity, where it is the change in enthalpy with respect to temperature while holding the pressure constant. Right? So we're just separating the variables here and integrating it. Move the dt to this side. When you integrate the dH, you just get delta H, and that's why it's the integral from T1 to T2. All right? So we've talked about this a lot. In your table, I think it's called B2, but this may have changed based on my dinosaur addition. Right? They have correlated the ideal gas heat capacity. Now you will talk more about how to do a non-ideal gas heat capacity in Thermo 2, but for this is the ideal gas contribution. So this is just a single isolated molecule. How much energy does it take to heat it up, right? If we want to get C sub V, right, this is equal to C sub P minus R. So if we look at the units, this unit A has the joules per mole Kelvin. So what you would do if you wanted to get C sub V is you would take A minus R from the tables. That's how we can get the C sub V. Or you can just calculate the C sub P and minus R at the end. Right? but just making sure you do your algebra correctly. This comes from dH equals the change in du plus the change in PV, right? So H is equal to U plus PV. So if I just take the differential of all that, right, for a very small change in H, a very small change in U, a very small change in PV. If we put this over dt, 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 right, this just comes to C sub P equals C sub V. PV equals RT. Oops. So if I take the derivative of PV with respect to T, it's just equal to R. Right? And this is only valid for the ideal gas law. Yes?
If it's not important, you can ignore the question, but you said A minus R is CV.
So if you take this correlation here, and you want to, instead of calculating C sub P, you want to take C sub V, you take this A value and you minus R from it, and then you just go about your calculation.
Okay.
That will give you the C sub V correlation. Right? Because if I plugged in some arbitrary temperature like 200 Kelvin, 200 here, 200 here, 200 here, and I crunched it, that would give me the C sub P. Then I just need to take C sub P minus R, and that's the C sub V. But I can either take that away from A at the beginning, or I can take it away from the whole thing at the end. It works out the same algebraically. Right? So for a lot of non-ideal fluids, right, the derivative of PV is not just going to be equal to R. Right? So this is only true for an ideal gas. If it's a non-ideal gas, this is a much more complicated term, and something that you guys can look at in your future thermo classes. Okay. So for gases, this is for ideal gases only. For solids and liquids, heat capacity, C sub P and C sub V are almost the same. Right? That's because the PV contribution in the enthalpy term is really quite small. So unless you get to hundreds or thousands of atmospheres, this is going to be a reasonable way to handle things. Right? So in this case, then, the U is approximately the H for solids and liquids as well. For pressures less than maybe 1,000 atmospheres. That's because they're relatively incompressible. Now we can approximate how bad this accuracy is, and I've got an example where we'll show that. But it's an example you've also done in the homework when you went to like 1 to 5 atmospheres pressurizing. I think it was ammonia. I want to say homework 5. So for an ideal gas mixture, right? The principles of an ideal gas is that the molecules don't know that any other molecules exist. So then there's no interactions between the molecules. So to approximate the heat capacity of a mixture, it's just a weighted average of all of the individual contributions, such that we get the C sub P of the mixture is equal to a weighted mole fraction of the individual heat capacities. Now this is exactly equivalent as if you had just heated each of the fluids up independently. But if I had 5 moles of one thing and 1 mole of another and 2 moles of another, I could just figure out how much it takes to heat up A, then B, then C. But it works out to being the same as if you just take a weighted average of the heat capacities as well. Algebraically, it would be the same. Right, so you can integrate this, or you can do each of them individually. Okay. So I've got an example here that we can work through. And this will be very similar, like I mentioned, to one of those homework problems. So we're going to have 1 mole per second of benzene. It's going from 10 megapascals and 20 degrees C, going through a process where we are putting in heat to 200 degrees C and 1 bar. So effectively 1 atmosphere pressure. Our energy balance change in enthalpy is equal to how much heat we put into the system. Out minus in, multiplied by the flow rates. So this could be in units of kilojoules per second, kilojoules per second, kilojoules per mole, multiplied by moles per second, kilojoules per second. Units are good. So the path that the fluid may take is not necessarily the path that we need to take. So if I look at a PT phase diagram, low temperatures, high pressures, solid, low pressures, high temperatures, vapor, somewhere in the middle is going to be liquid state. What is this point right here? Critical point, TC, PC. So we're going to start off at some pressure that is going to be high pressure, relatively low temperature, and the path may go somewhere to like this, right? We don't exactly know how they designed the specifics of the process, but we don't have to follow exactly the same path. Enthalpy is state function. We just need to go final and initial. So we're going to break this up into simplified steps. 1 is going to be delta H1, delta H2, delta H3, and delta H4. Who here has taken calculus 3? Did you guys do double integrals? How fun are double integrals?
No.
No fun. If I take this path, okay, I have a gradient in P and I have a gradient in T. That would necessitate me doing 2 integrations. If I choose my path, so I first go isothermal, that means I only have a gradient in P, which is a single integral. Then I go isobaric, a single integral. I vaporize, and then isobaric as well. So by choosing a path along constant pressure or constant temperature lines allows me to avoid double integrals. This is why we set it up like this. Could you integrate diagonally? Absolutely. Would it be pleasant? Absolutely not. Okay? So our energy balance then, delta H, which is equal to our heat in, is going to be the flow rate multiplied by delta H1 plus delta H2 plus delta H3 plus delta H4. Okay? We're going to break it up into all of our steps. Yes, question?
In this case, we couldn't integrate we couldn't take a different path where we kind of go outside of the critical point and then down to it?
Absolutely, you could. We could go like this too. Totally possible.
So by doing that, would we take out a delta H?
I think that the critical point of benzene is higher than 200 degrees C, so we would still have to vaporize it. But if we choose this path, we can use tabulated values for the heat of vaporization because we're going to do it at 1 atmosphere pressure. If we took this path, we would need to have access to the heat capacity of liquid benzene at elevated pressures, which we could probably assume is pretty constant. We're going from, this is 10 megapascals, so that's like 100 atmospheres. We could probably ballpark it. Then we would depressurize it once it has a higher temperature, and we'd have to estimate the heat of vaporization at 200 degrees C to get to that point right there. Totally acceptable pathway, right? The only thing that limits us is access to the data. If we have data of the heat capacity at every pressure, at every temperature, at every phase, we can choose any path we want to. That's a very good point. Thank you for bringing it up. All right. So I'm going to hammer this out because we've seen this before in the homework. The specific gravity of benzene is 0.879. What does that mean its density is?
0.879 kilograms per liter.
Okay, what's another unit?
Kilograms per meters cubed.
Could do that one. So what would it be in kilograms per meter cubed?
879.
Okay, what about another unit? What about 0.879 grams per milliliter or grams per cubic centimeter, right? So the reason why we communicate specific gravity is because we can pick and choose. Now, if you were experts in the American engineering unit system, you could remember how many pounds per cubic foot water's density is or how many pounds per gallon water's density is. I don't remember that. So that gives us that our density is 879 kilograms per cubic meter, and it will become clear why I chose these units to work with. Okay, so for delta H1, it's going to be P delta V. Because if we look at our enthalpy, I don't have the enthalpy definition up here, right? But enthalpy right? So we're going to consider only this contribution here. So technically, these two variables are functions of pressure, but that involves nasty, non-ideal calculations. So for the pressure calculations, we're only concerned ourselves with this one here. But these two properties are functions of the temperature, but they're kind of weak functions of temperature for a liquid. So we're going to neglect that. And we're only going to focus on this one here. So if I want the delta H, the pressure is constant. Oh, sorry, no. Pressure is not constant. Backwards. We're going to assume that the density is constant. And we're changing the pressure. So we're assuming it's incompressible. So V hat equals constant. That equals incompressible. We are assuming this. Is this accurate? Reasonably. Is it 100% accurate? No. We would need to have the density at every single pressure, and then we could integrate this expression just like we integrate the C sub P. Right? So the more accurate way would be integrate from state 1 to state 2 V dP. Right? That would be the more accurate way to do it. But are you seeing parallels behind this compared to the heat capacity calculations? Right? So we're unpacking real data. So if we had the density or the specific volume at all the different pressure states, we could assume this is constant. Integrating dP is just P2 minus P1. Or if we had access to the data, we could integrate this numerically. If we had an equation of state that gave us a specific volume, we could integrate that function, right? So what we're doing in thermodynamics is we're unpacking data that someone has generated for us. And the good thing about thermo that I think is an underappreciated gem is that we can measure things as simple as how does the density change versus pressure. And that actually contains all the information that we need to know about our energy balances, right? So that's the cool thing about thermo. I think it's cool. No one here thinks it's cool. All right, so we first need to find the specific volume. The density, the molecular weight, hopefully my units cancel out, meters cubed per kilomole, 0.0889. So then I can calculate the delta H. Delta H1 is equal to V hat P2 minus P1, which is equal to this value here, 0.0889 meters cubed per kilomole. Final pressure, 10 to the 5 pascals minus 10 to the 7 pascals, right? 1 bar is 10 to the 5 pascals. A megapascal is 1,000,000 pascals. So 10 megapascals would be equal to 10 to the 7 pascals. The reason why I chose kilograms per cubic meter is so I could have cubic meters here. Cubic meter pascal. What is a cubic meter pascal? Joule. Meter cubed pascal is a joule. So that gets my delta H to be minus 8.80 times 10 to the 5 joules per kilomole, which is equal to minus 880 joules per mole. All right, I got one of my delta H's knocked out. Yes?
I was just a bit behind in writing. It's 10 to the 5 PA minus 10 to the what? PA?
7.
Where did you get the 10 to the 7 from again?
So that is from here, 10 megapascals. So 1 bar is 10 to the 5 pascals. So a megapascal, so 1 times 10 to the 6 is 1 megapascal. 10 of those is 1 times 10 to the 7.
Okay, then where do you get the 10 to the 5th?
That's the final state, 1 bar, 10 to the 5 pascals. So 1 atmosphere is 101.3. So the bar, they just drop the 1.3 out of it.
Okay.
So that's why they choose that one there. Okay. So what we're doing here is we're doing this depressurization step just once. So we're getting it to this final 1 bar pressure, and then we just have to worry about heating isobarically. Okay. So the other ones are pretty straightforward. So what I'm going to do is use the heat capacity of the liquid at 50 degrees C. So this is the average temperature of that first step, right? Because we're heating from 20 to the normal boiling point. And the normal boiling point for benzene is 80.1 degrees C. So the average temperature is going to be 20 plus 80.1 minus 20 over 2, and that works out to be about 50 degrees C. So that's the average between those 2 points. Right, so this is the length of the line segment, 80 minus 20, and then I shift it to the starting point. And that's how I can get the average temperature. So in this case, my delta H2 is going to be C sub P multiplied by T2 minus T1. If I find appropriate data sources, 139 joules per mole Kelvin, 80.1 minus 20, I get a value of delta H2, 8.38 kilojoules per mole. And to reinforce why we oftentimes neglect the PV contribution, this is less than 1 kilojoule per mole. This is almost 10 kilojoules per mole. Right? So going from 100 atmospheres to atmospheric pressure, it is less than it takes to heat it up 60 degrees. right? So much, much smaller contribution. Okay, delta H3 is just the heat of vaporization at the normal boiling point, because we are going through 1 atmosphere pressure, or 1 bar, which is close enough to 1 atmosphere pressure. This is a value that is already tabulated. So we can just simply look this one up, 30.765 kilojoules per mole. And lastly, we're on to our final stage. So we have depressurized, delta H1, heated the liquid to the normal boiling point, so a saturated liquid, that's delta H2. We have vaporized it, that's the heat of vaporization, delta H3. And lastly, we have to heat the vapor from the normal boiling point to the final condition of 200 degrees C. Again, I'm going to use the average temperature. So this is going to be the heat capacity at, what did I find the average temperature was? 140 degrees Celsius, 115.5 joules per mole Kelvin. So if I plug this in, I get 13.8 kilojoules per mole. Okay, I have said it a bunch of times. The energy balance is not the hard part of the thermodynamic calculations that we're going to do. The hard part is choosing a path, finding the data, and manipulating the data in order to extract out delta H's and delta U's. I plug all of these values together, and I get my final answer of Q is equal to 52.1 kilojoules per second. Is how much heat I need to complete this process. Okay. How does everyone feel about this? You've done similar problems on the homework, but what are the pinch points? Question.
Were we just getting some p-values from some table or something?
Yes, so I believe benzene actually has in the Felder book a temperature-dependent heat capacity correlation. Not all liquids will have a temperature-dependent heat capacity correlation, but common ones generally do. And if they're not in the back of the book, you can also look up different resources. There are companies that have databases that organizations pay tens of thousands of dollars a year to access, where all they do is scour the literature and find measurements of these different thermofluid properties. So the glory days of chemical engineering, like 1950s to 1980s, right? This is where a lot of the textbooks that we use were written. This is where a lot of the data was generated, right? So the Peng-Robinson equation of state is only from about the 1970s to early 1980s. Right? That was only possible once enough property measurements were made that some authors could get together, correlate it, and build one nice uniform equation of state. People are still developing equations of state. People are still measuring thermofluid properties. One of my PhD students just got a job at Dow Chemicals. His job is to improve their thermodynamic modeling of polymer properties. Right? So there is still money and job opportunities in this exciting field of thermodynamics. But I promise, if you get good at this, there will be lots of job opportunities because most chemical engineers hate thermodynamics. But it really is an elegant curriculum. Okay, any more questions? Yes?
So on the top right whiteboard, chalkboard, you used the one equation, and then for the delta H, and then on the bottom one you used a different one. But we were just saying how they're pretty much the same in this scenario. Right?
Which part did I use a different equation on?
Didn't you use a different delta H equation? Or no?
Oh, this one here? Yeah, so let me just go over that really quickly again. This is the case because I'm doing this isothermally. Okay, so U and H U and H are weak functions of pressure, specifically C sub P and C sub V. C sub P and C sub V are mostly a function of temperature. They are technically functions of pressure, but they're relatively weak functions of pressure. And in order to assess how much heat capacity changes at different pressure states, you have to use a non-ideal equation of state. And so the problems get much, much more challenging more quickly. So if we assume, right, that we're only modeling the heat capacity using like an ideal gas heat capacity model, then there is no pressure dependence. So the assumption we're making in the first step is that we're doing it isothermally, so we're ignoring the pressure effects of the heat capacity. So when we're looking at the enthalpy, right, this here is the integration of the heat capacity C sub V. This term right here is what we're not neglecting. So it is a simplification of the process. Okay. So in this scenario, we just broke down our pathway into steps. Each of those steps had their little bit of quirks, but, you know, really, we have depressurizing a liquid and then heating. Right? So the one quirk that we have to remember is depressurizing a liquid. Isothermally, we can use this expression here. For heating, it's still the same expression, integrating heat capacity. Okay? So we did 3 different things. Depressurize the liquid, heat a fluid, heat a fluid. That's the same thing, just with different heat capacity values. And then here, we vaporized it. Now, we chose a path such that we went through 1 atmosphere pressure, so we could just look up that value. Now we're going to talk about if we choose a different path. Question over here.
So basically on that first depressurization, you're saying that U is pretty much constant, so we can just neglect it for taking the difference of H1 and H2?
Correct.
And then on the next ones, we're saying that PV, change H2, change H3, change H4, we're saying PV is practically constant, so we can neglect it and just calculate the U portion of the enthalpy?
So for the liquid state, yes, right? For the liquid state, if we assume it's incompressible, the pressure is constant, the volume is constant, there is no delta PV. Now for the gas phase, that's not the case, right? Because if I change the temperature, I change the density. However, for an ideal gas, PV is exactly equal to RT. And if we do this, right, so this is what's coming into, this is where that contribution comes into all that. And that's the difference between the C sub P and the C sub V.
So on change H4, could you change the integral of CV delta T times RT, or plus RT, sorry, instead of doing the...
Yes.
Okay.
Yes, and that's exactly the derivation of
The C sub...
wherever I have it here. This, yeah,
So that's just incorporating that PV term, so we don't have to...
Yeah, so,
Okay.
right, we can replace this with RT. I can take the derivative of this with respect to temperature, and then I get C sub P equals C sub V plus R, right? So I'm taking the derivative of RT with respect to T, and that's R. So it's all contained within there. Okay. So let's talk about physical properties. Does someone bravely want to volunteer what happens at the critical point? Oh, back here we have volunteer.
I said liquid and gas.
Exactly. So if I had a critical fluid, what should the heat of vaporization be? 0. Correct. Right? So if I were to look at a chart here of enthalpy versus temperature, right? And I'm going to say this is the critical point right here. This is Tc and Pc. This should give me the enthalpy of the vapor equals the enthalpy of the liquid, correct? The properties of the liquid and the vapor are identical at the critical point. So that would mean that the delta H of vaporization at the critical point has to be equal to 0. So now, if I were to choose, let's say, for example, 20 degrees C down here, and I want to draw 2 data points, one for the liquid, one for the vapor. Does a liquid have a higher enthalpy, or does a vapor have a higher enthalpy? Vapor, right? Because heat of vaporization is always positive. Final vapor minus initial is a positive number, right? Delta H of vaporization equals enthalpy of the vapor minus enthalpy of the liquid. If delta H vaporization is greater than 0, that means the enthalpy of the vapor is always greater than the enthalpy of a liquid. Right? That's why when you put your hand over your pot of boiling water and steam is coming out, it's not cold, it's hot. Right? So that would mean that I could draw one point here, and let's say this is the enthalpy of the vapor at 20 degrees, and one point down here is the enthalpy of the liquid at 20 degrees. The difference between these two lines is the delta H of vaporization at 20 degrees C. Does that make sense? So, as I increase the temperature, right, following the vapor pressure, I'd have to also increase the pressure, right, if I wanted to keep a saturated liquid and a saturated vapor. As I increase the temperature and increase the pressure, and I maintain a saturated mixture of vapor and liquid, should my heat of vaporization increase or decrease as I get closer to the critical point? Decrease, right? So I can just connect these dots as an approximation. As I get closer to the critical point, it gets easier and easier to boil or vaporize my fluid because the properties of the liquid and vapor slowly get closer together. So this case right here, let's say this is T equals 200 degrees C. This difference here would be the delta H of vaporization at 200 degrees C. It gets smaller and smaller and smaller. Okay, here's another question. This chart has the information to answer it. What has a higher heat capacity? Liquids or vapors? Okay, I have one vote for vapor. I have one vote for liquid. Who's the winner? Okay, so I have a lot of people saying team liquid. How do I know what the heat capacity is based on this chart right here? What is the definition of heat capacity? Yes?
Well, heat capacity is like the amount of energy you need to put in something to raise it a certain increment of temperature.
Mm-hmm.
I guess from like a physics perspective, you can say, well, the water's like takes more energy because it's all, you know, it's not ideal gas, so all the molecules are interacting, so it's going to be harder to get them to move. Whereas a gas, it's already moving, so it's easier to just keep it moving.
On the right track. So I'm looking. So you're talking more about the molecular origins of the heat capacity. Back here. Yeah.
Wouldn't the CP be related to the slopes of the pH values?
Exactly, right? C sub P is defined as the gradient in temperature, the gradient in enthalpy with respect to temperature. Now, technically, this is at constant pressure, right? So we are changing the pressure here. So this is not a 100% accurate analogy, but it's a good descriptor, right? So we have the rise over the run, the rise over the run. The liquid has a higher slope, so that means the heat capacity of the liquid is going to be higher than the heat capacity of the vapor. And this makes sense, right? Because think of liquid and vapor as running a race. And vapor is starting off way further down the road. So in order for liquids to catch up so that their enthalpies meet at the critical point, having the same enthalpies, the liquid's got to run a whole lot faster to catch up to it, right? So that's why a liquid is generally going to have a higher, it may be universal, always has to have a higher heat capacity. Now, the reason behind that is that there's energy stored in the configuration of molecules. So when I heat the system up, not only are the velocities increasing, right? So the velocity of the molecules in this table here are actually the same as the velocity of the molecules in the air. But they're just jiggling back and forth really, really quickly. Whereas these ones are just shooting off up in the distance, right? So the temperature is the velocities of the molecules. But the difference between liquid energy and vapor energy is that in between the liquids there is attraction and repulsion. So if I want to heat my fluid up and expand it, that means that I have to take two water molecules that are really close friends that like to be near each other, and I have to slowly pull them away on average. And they don't like that. They want to be close to their friends. So they says, you know what, I will go away from my friend, but you got to give me a little bit more energy, right? You got to sweeten the deal, right? So it takes the water molecules a little bit more energy to move away from their friends. That's where that extra heat capacity contribution comes from in liquids. So this drawing that I've provided here is actually sort of the formulas that I was kind of writing down on the board when we came in. So I have a way of estimating the heat capacity that's a little bit involved. I'll give you the cliff notes of it. And that is to use the Clausius-Clapeyron equation. And this is actually how they measure the heat of vaporization. They don't actually measure it. They just measure the vapor pressure as a function of temperature. So we have the Clausius-Clapeyron. Clausius-Clapeyron equation, d ln of the vapor pressure dt is equal to the minus delta H of vaporization over RT. Now we can integrate this expression here to make it a little bit easier for us to think about it. We can get the natural log of the vapor pressure is equal to minus the heat of vaporization over RT. Oops, I missed a squared here. All right, so if we integrate this, we lower the power, negative sign, right? So hopefully that's an integration that we're comfortable with. Just the integration of a polynomial, just with a negative power. Plus our constant of integration. So we can look at this. Yes?
When you integrate that, wouldn't it be around a negative sign?
Correct. I didn't mean to draw that. Oh, actually, no, I have these screwed up. This is not negative. This is negative here. Sorry. That's the right way. So what we could do is we could write this, right, as a linearized form. So if we were to plot the natural log of the vapor pressure versus 1 over the temperature, the slope of that line would be slope would be equal to negative delta H vaporization over R. So this is how they actually measure the heat of vaporization. They don't measure it. We have such high confidence in the Clapeyron equation that we don't even bother measuring it, because we know theoretically that it has to be this. So if we measure the vapor pressure as a function of temperature, we can measure the heat of vaporization directly from that. So if we had, let's say, does anyone know of a formula that we have that tells us what the vapor pressure is? Anton's, right? We could just plug all this information in from Anton's and take the slope of it, right? That tells us the heat of vaporization. That's one way to do it, albeit it's a skosh bit cumbersome. But you could write your own code in Excel or MATLAB to do this, and then plug in any arbitrary Anton's parameters, and boom, it'll spit out the heat of vaporization, right? This is generalizable, right? So any arbitrary set of Anton's equation parameters, you could write your own software that just spits out the heat of vaporization at any arbitrary point. Question?
How come we are integrating delta H back with respect to T?
Oh, you mean like if this is changing as a function of temperature?
Yeah,
It will be a function of temperature. So this value doesn't have to be constant necessarily. I'd have to go back and think about my calculus here. But I know this works. But I don't know if I have a good explanation for why I'm doing my math the way that I'm doing my math. Yeah. Because this is just the opposite of what they do to actually measure the heat of vaporization. So I guess the assumption would be at some temperature, heat of vaporization is constant. Around that neighborhood, this is appropriate. But yeah, don't have a super good answer for that one right now. Okay, so this is one way to do it. I have on the board here a couple of other different things, and I'm going to fill in two more formulas that I didn't have a chance to pre-write. So effectively, there are ways that people have come up to estimate these properties following the corresponding states principle, right? Basically stating that every fluid behaves similarly relative to its critical point. And so these rules are all developed based on that assumption. So there's a thing called Kopp's law, where you can estimate the heat capacities of solids and vapors. For my version of Felder, this is 8.3c and table B10. It's a group combination theory, so basically saying what is the composition of your material, how many carbons, how many nitrogens, how many silvers, so on and so forth, and then estimating the heat capacity from there. This is Troughton's rule, Troutons. This is estimating the heat of vaporization to plus or minus 30%, so not particularly good, right? It is 0.088 times the boiling point in degrees Kelvin for nonpolar systems, or 0.109 boiling point in Kelvin for water or low molecular weight alcohols. Another one that is very friendly that students love is the Watson correlation. So the Watson correlation is the heat of vaporization at some temperature 2 with respect to the heat of vaporization at temperature 1 is the critical temperature minus T2, critical temperature minus T1, 0.38 power. So if you know the normal boiling point's temperature and heat of vaporization, this is a correction factor to basically slide you up or down this scale here. There's one more that is fairly accurate. Shen's rule is generally plus or minus 2%, so pretty good, but the formula is much less pleasant. So these are all in kilojoules per mole units. Okay, so bear with me. This is the last thing that I'm going to write before we're done on class. The boiling point, these are in Kelvin. (0.033 TB over TC minus 0.0327 plus 0.0297 log base 10 of the critical pressure. And I have to check, actually, I don't have it in my notes what units the critical pressure is supposed to be in, so I'd have to look that up. 1.07 minus TB over TC. So I don't have here, I got to look this up, but it's also in your textbook, this Chen's rule. Again, this is a big correlation of lots of different materials, and they found that this form fits a lot of the data reasonably well over a large temperature range. Question?
Is that TB the boiling point at 1 atmosphere? Or
Correct, the normal boiling point, yeah. So TB is the normal boiling point, TC is the critical point. In this correlation, K is Kelvin for temperatures, but I did not write down in my notes what the PC is. Most of you will probably find the most utility out of the Watson correlation. Yes?
And is there a plus or minus percentage for Watson or no?
I don't have it in my notes. The textbook might have more details. It may not have told us. All right. So quiz on Friday. And we're just in the thick of energy balances for the next little bit. All right. Oh, yes, good point. Yes, I will do that.